Welcome to displacement, average speed, and average velocity. This sheet has been designed so that I want you to try this page first of all. So all of question number 1, A, B, C, D, E, and F. Give it your best shot, and then see how you do compare with my answer. So if you're watching the video, hit pause now and give it a shot, or even hit stop and come back. All right, the first question has a motion map and we're supposed to describe the object. I tried to have a really nice answer here. I said that it is moving at a constant velocity. I know this because these arrows are all the same length, because it told me that the object is moving, or that the dots are 1 every second. So I put the delta t equals 1 second in there to make the motion map nicer. From that I know that it is moving 2 meters in every second, so it is a constant velocity of 2 meters per second. I know that it starts at the origin because this is lining up with the 0 meters, and it travels for how many seconds? Now just be careful, don't count the dots, but count the jumps. So that would be 1 second, 2, 3, 4, 5. So it travels for 5 seconds. So just be a little bit careful. You're not counting the dots, you're counting the intervals, the number of seconds that have elapsed. Okay, so our next part is to put this down in a position versus time graph. In order to make it fit, I went by 1s for my time axis and I went by 2s for my position axis. And for position, I'm going to be using the letter X because it's horizontal motion. Here are the dots that were represented by all the dots in the motion map. And then I can draw a straight line. I'll see how I do. That's not a bad straight line. So I should stop at 5 because that's how far the motion map goes. I really shouldn't extend the line because I'm not really sure what it does after 5 seconds. Now looking at the velocity time graph, how to go from this to velocity is I'm looking at the slope. So since this is a nice straight line, it's constant velocity, I'm going to have a horizontal line because the velocity is staying the same. So what is the slope? Well, if I pick any 2 points here, the rise over the run, that's the slope. So this goes up by 2 meters and it goes over here by 1 second. So the slope is 2 meters divided by 1 second, so it's going to be 2 meters per second. So when I label this, I'm going to label that 1 and 2. And let me just make sure I don't go too far here. If I label the time 1, 2, 3, 4, 5, and 6. Again, I need to be a little bit careful not to go past the 5-second mark. So that would be my velocity versus time graph. When I write a mathematical expression that represents the relationship between position and time, well, again, so I'm going to be looking at this one. This is the graph on the left is my position versus time. If I start off and think of it, well, if it's a straight line, I'm going to be using y equals mx plus b. In this case, however, my y-axis is actually labeled x. So I put x for position. The slope is 2 meters per second. In parentheses, the x-axis is time, and the y-intercept is 0. So I'm good. I can just leave it like that. From the position time graph, find the displacement from 1 second to 3 seconds. Okay, so if I'm looking at my position time graph, here I'll get a different color here. So this is my position at 1. Here's my position at 3. So my position here was 2. My position here was 6. So how much does it change by? The displacement is the change in position, or you could say it's the second one minus the first one. We don't have to get too complicated here. We can just say it's going up by 2. It's going up by 2 jumps, but from 2 to 4. So this is it increases by 4 meters. So I can say it's going to be 4 meters. I could actually say it's 6 meters minus 2 meters equals 4 meters. If I want to show lots of work, that's kind of nice. Find the under the VT graph from 1 second to 3 seconds. Okay, so looking over at the VT graph, the area from 1 second to 3 seconds, I guess it would kind of be this shape right here. So looking at that, How do you find the area? Well, it's the two dimensions. So this side here would be 2 meters per second, and this side here, so from there to there, this side here, well, it's not the 1 or the 3, it's the change in the time. So in other words, it's going to be 3 minus 1, so it's going to be 2 seconds. So how long is that side? It's 2 seconds. So really when I'm answering this question, it's going to be the area, kind of make a little box here, so it's going to be 2 meters per second times 2 seconds will give me 4. Now the seconds cancel each other out, 4 meters. So proving once again that the area under the VT graph represents displacement. So it is displacement, otherwise known as the change in position. Now, if you haven't done so yet, I want you to turn to this next page and give this page a try on your own now. So hit pause or stop and then come back when it's all done. All right, so here is our position versus time graph. To make the velocity versus time graph, we have to look at each of these different segments. The whole thing is in constant velocity, but we can think about each segment as a separate section of constant velocity. So the first one has a slope of 2 and it's going uphill, so it'll have a positive 2 slope like that. Now we have a second where it's horizontal, which is a slope of 0. Put that line over top, and then we have a section where it's a slope of positive 3, and then we have a section where it's 0 again. Actually, I'll try to put that right on the line, and then here this is 0 again, and then we have 2 seconds where it's going downhill, so it's negative, and it has a slope of -5. Stopping at 9 seconds here, at 9 seconds. Okay, and now draw a motion map. I've put in my delta t equals 1 second, indicating that each dot is equal to a change in time of 1 second, and I'm starting over here at t equals 1. And I did my scale units by 2 meters so I can get it all in there. You'll notice at the very end, I don't know whether or not, I don't know what's happening with this graph. Does it keep on going down like this, or does a person stop after that? So I kind of like to put the arrow on there to say, well, at that point is part of this line which is going downhill, so they're going -5. But a person could make the argument that we don't really know whether or not it stopped at that point or whether it kept on going. So sometimes what I like to do is just put sort of a dotted line to say, I think it was part of that motion, but I don't know. I would let anything go correct. That's not something I'd be looking for. So don't worry about losing a mark if you add the arrow or don't add the arrow. But everything else I think should be pretty close to what I did. Determine the displacement from 3 to 5 seconds using the velocity versus time graph. So from 3 to 5, that's this area right here. So looking at that rectangle, that would be, well, let's see here. This is 3. So this side is plus 3 meters per second, and this side is 2 seconds. So it's going to be 3 meters per second. Oh, come on over. 3 meters per second times 2 seconds. So I'm going to get 6 meters. And that is the displacement. I'll put it in like that. Okay. Determine the displacement from 7 to 9 seconds. Okay, from 7 to 9. Now, this is over here. And I wonder if you caught this. Now, this side here is actually, this is a negative 5 meters per second, and this is 2 seconds. So when I write this here, I'm going to say delta x is equal to negative 5 meters per second times 2 seconds. So again, the seconds cancel out, and I get minus 10 meters. I like putting boxes around my final answer. So it went in a negative direction, so that's why it's negative. Determine the average velocity from 4 seconds to 8 seconds. So how do you find the average? Well, it's going to be the displacement during that period of time divided by how much time went by. So the how much time went by is kind of easy. Between 4 seconds and 8 seconds, 4 seconds goes by because 8 minus 4 is 4. But what was the position? What was the displacement, the change in position? Well, let's look at it. At 4 seconds, this is 4 seconds, it was at 7. Okay, and then at 8 seconds, here's 8, 6, 7, oh, here's 8. At 8 seconds, it was at 5. So it actually went from here down to there. So what was the change in position? The change in position, well, it went downwards by 2. So I will say here that it was minus 2 meters. So 2 over 4 is the same thing as a half, so I'll say negative a half meter per second. And sure, you could put it in decimal form if you want to put negative 0.5. Determine the average speed. So average speed is going to be equal to now not displacement, but now it's going to be distance divided by how much time went by, the change in time. So again, from 4 to 8, it's still 4 seconds. But what was the distance? Okay, so looking back at this graph, here, first they went up this way, so they went plus 3. Or actually, I should just say 3, because, oh, darn it, I got to draw that again. I erased my green line. Okay, so from here to here, it moved 3. The object moved 3. Here, the object didn't move. From here to here, now be careful, even though it went in a negative direction, we're talking about distance, which doesn't worry about direction. So we're going to say from, I guess, what is that, 7 seconds to 8 seconds. There it moved another 5 meters. So in total, traveled 8 meters. So it's going to be 8 meters divided by 4 seconds, so it's 2 meters per second is the average speed. Okay, so I hope that really helped. Now I gave you a practice sheet, and you can check your answers on the practice sheet. On the last page is an answer key. All right, thank you, and I'll see you in class.